Welcome to the Deep Dive. Today we're peeling back the layers on something pretty significant that's reshaping the AI landscape. Our mission, as always, is to cut through the noise, get you the key insights so you can really grasp what's happening right at the edge of AI infrastructure. We're diving into the recent news about NVIDIA Blackwell, specifically its debut on Amazon Web Services. We're talking about the new Amazon EC2 P6 and the P6e Ultra Server instances. Look, if you're interested in the future of AI training inference, this is a really pivotal moment.
Yeah, it's fascinating because you see, AWS isn't just like plugging in faster chips. They're really architecting the whole foundation. It's about tackling all the bottlenecks, especially for these huge demanding models, what people are calling frontier AI at scale. This deep dive, I think, will really show the unique engineering that's making it happen.
Okay, so let's start right there. What is NVIDIA Blackwell and why is landing on AWS such a big deal right now? It feels like a new chapter.
Fundamentally, Blackwell offers these pretty substantial leaps. Performance, cost efficiency, energy efficiency, the whole package. Think of it like a massive accelerator. It lets developers tackle problems that were just, well, impractical before. And the key number everyone's talking about, up to 30 times better performance than Hopper for large language model inference. That sets a new bar in the cloud.
30 times. Wow. Okay. And AWS is bringing this power online in two main ways, right? There's the EC2 P6 instance, uses NVIDIA's HGX B200, but then there's the big one, the EC2 P6e Ultra Server. That's got the NVIDIA GB200 NVL72, and AWS calls it their most powerful EC2 instance ever.
Right. And the GB200 NVL72, you have to understand, it isn't just a chip. It's designed as a whole system, a rack-scale, liquid-cooled supercomputer. What's really amazing is how it lets 72 of these Blackwell GPUs act like a single massive GPU. Think about what that means for developers. It radically simplifies programming for these enormous models. Instead of juggling dozens of GPUs, you treat the whole rack as one engine. That's a total game changer for training and running inference on the latest frontier models.
Okay, so you concentrate all that power. The next problem is communication, right? Getting data moving between all those units. And modern AI, especially this agentic AI stuff, it just demands incredible bandwidth. You need to scale out across servers and scale up within one server.
Precisely. And that's where AWS has put a lot of thought in. They've got this sophisticated dual networking strategy, tackles both sides of that coin.
So for scaling out across different servers, they're using their own tech. The Elastic Fabric Adapter, EFA, powered by the AWS Nitro system. That gives them, what, 28.8 terabits per second per Ultra server? And you can build these massive EC2 Ultra clusters, hundreds of thousands of GPUs potentially. But how do you keep that reliable at such an insane scale?
Yeah, that's where Nitro really makes a difference. See, EFA runs over something called Scalable Reliable Datagram, SRD. It's AWS's own networking protocol. Think of SRD like a super smart GPS for data packets. It doesn't just find the shortest path, it maps the whole network, finds the most reliable route, and if there's a hiccup, it instantly reroutes. Like real-time traffic avoidance for your AI compute. So it routes around failures, avoids slowdowns, avoids downtime. Absolutely vital when your training job takes days or weeks.
Okay, that's scale out. Then within the single rack, the scale-up network, that's connecting all those GB200 trays together.
Exactly. That uses NVIDIA NVLink, creates this tightly coupled mesh, a single 72 GPU NVLink domain. And the bandwidth there is just staggering, 132 terabits per second, all inside one Ultra server.
Wow. How does AWS manage something that complex, that high speed within the rack?
Well, they leverage their Nitro system again. They use a Nitro-powered head node. Normally managing NVLink needs specialized, dedicated hardware that can add latency, points of failure. But here, the Nitro head node, which is already super efficient at virtualization and offloading tasks, handles orchestrating that NVLink traffic. It means fewer separate devices, less complexity. And it's all managed within that secure Nitro-trusted domain, which boosts reliability and control.
It keeps coming back to Nitro, doesn't it?
Yeah.
So in AI, things change fast.
Yeah.
How do you keep everything reliable, secure, updated without messing up people's work? That seems like a huge challenge.
It is, and that's another area where Nitro provides a key advantage. It's about observability. Nitro gathers way more telemetry, logs pretty much everything about the hardware. This gives AWS incredible insight. They can spot potential failures, sometimes even before they happen. For you, the user, that means maximizing reliability, security, performance, especially critical for those marathon AI training sessions.
And that deeper insight enables something AWS calls live updates. They say it's pretty unique. Why is that such a big deal for someone running a long AI job?
Right.
What's the magic there?
Right. So typically, cloud providers have this tough choice, right? Keep infrastructure running 3/4/7, but maybe skip firmware updates. Or take things offline for updates, which could interrupt your work, maybe even kill your job.
Yeah, nobody wants their week-long training run kicked off.
Exactly. But with Nitro, AWS can do live updates. They can update system firmware transparently while the system is still running. So your crucial AI workloads just keep going. No interruptions. And you benefit from constantly improving reliability, security, performance. No downtime needed. It's like performing open heart surgery on a live server. Complex stuff. But the payoff for continuous AI work is huge.
Okay, so we have massive compute, smart networking, reliable updates, but cramming all that GB200 power into a rack creates heat. Lots of it. And you mentioned liquid cooling. AWS said this was a first for them at this scale. They couldn't just use off-the-shelf stuff.
Yeah, they hit some roadblocks there. Building brand new liquid-cooled data centers takes years. Too slow for Blackwell. And the existing market solutions, they often didn't scale well enough, or they took up too much precious floor space, or they required huge changes to the data center itself, maybe used way too much water, just didn't fit AWS's needs for scale, speed, and efficiency.
So
Yeah.
they invented their own solution. Typical AWS.
Pretty much. It's called the In-Row Heat Exchanger, or IRX. And the goal was really the best of both worlds. Super effective cooling, but also adaptable.
How does it manage that?
Well, the clever part is its design. It can be installed with no changes to the existing air-cooled setup in the data center, and minimal changes to the infrastructure overall. That's huge. It means they can deploy it fast in existing facilities and new ones, gets the compute power out there quicker. It's designed to scale fast, uses standardized parts, fix standard racks. Very practical.
Okay, walk us through how it works. If I'm a chip getting hot in that rack, what happens?
Right. So the IRX has three main parts: a water distribution cabinet, a pumping unit, and these fan coils. Cool liquid gets pushed from the pump to the servers. Inside, it flows through these special cold plates. AWS and NVIDIA co-design these right onto the chips, pulls the heat away very effectively. Then the warm liquid flows back to the IRX unit. It goes through coils, and fans blow air across them, cooling the liquid back down. The heat gets pushed out the bag into a contained hot aisle, then vented out.
You can scale it up or down easily.
Exactly. Unlike a lot of other systems, they can just add or remove fan coil units depending on exactly how much cooling that row of racks needs. Very modular, very efficient. It means, like they say, we don't need to design the data center around the rack. The cooling adapts to the compute.
It really is a complete system, isn't it? We see how it all fits together. The Blackwell power, the smart networking for scale out and scale up, the Nitro system for reliability and updates, and this custom cooling.
Yeah, it's a cohesive approach. And the immediate result for developers: support for over 900 SUDAX libraries, AI models, ready to go. It's available now for AWS customers, ready to drive breakthroughs in science, industry. The next wave of AI reasoning, it really enables these more complex agentic models.
How can you, the listener, get your hands on this?
You can go direct, use the P6 instances with the HGX B200, or the P6e Ultra servers with that beastly GB200 NVL72, or you can use AWS managed services like Amazon SageMaker Hyperpod or NVIDIA DGX Cloud. Different ways to access the power depending on your workflow.
It's just incredible the sheer engineering depth required to build these foundations for the future of AI. It really underscores that it's not just about, faster silicon. It's the whole intricate system making it work reliably at scale.
Absolutely. And maybe that leaves you, our listener, with something to think about. With compute getting this powerful, this efficient, this reliable, what problems can you solve now that felt impossible before? How do you see this kind of foundational shift accelerating innovation in your own field or just in AI generally? What new frontiers does this open up?